Hello and welcome to section 2.5. In this section and the next, the last two sections of this unit, we're going to apply some of Newton's laws to different situations and just talk about how they apply. So in this video, we're going to look at two situations. One, what happens in a car crash? We're going to apply Newton's first law of motion to things that happen in car crashes. And second, we're going to look at the motion of falling objects and how we describe that. So we're going to tie that in with our Newton's second law, force, mass, acceleration. What does acceleration do to gravity? What is the force of gravity? We're going to talk about air resistance, terminal velocity, and free fall. So let's start by looking at what happens in a car crash, and let's look at Newton's first law of motion. If we have our car traveling this direction, that is the motion in which it is traveling. And remember, objects in motion tend to stay in motion. And this object encounters another object at rest, maybe. It runs into a stationary object. And that object at rest is exerting a force in the opposite direction, in this direction, which causes this car either to completely stop or very rapidly accelerate in a negative direction, one or the other. As this car is being forced to have a change in motion, severe change in motion, because of that force being exerted on it. What's happening to all of the objects inside of the car? The passengers, things they might be holding. What's going on with them? Well, just as we said for the car, an object in motion tends to stay in motion. The same is true for everything inside of that car. Everything inside of that car was also traveling at whatever velocity this automobile was traveling at. So they will continue to try to remain in that same motion. They resist a change in motion. Therefore, it's really important to wear your seatbelt so that this doesn't happen, and so that or this as well. This person apparently is not wearing a seatbelt either. So the seatbelt holds you in, and so you are able to change motion along with your vehicle. An airbag, you guys know about those, another safety feature. Sometimes those can really help someone as well as they are trying to change motion very suddenly in the case of an accident or crash. It's a chemical reaction that occurs so fast that as the gas is released in this chemical reaction, this airbag immediately expands from that reaction, and that can cushion passengers as well and keep them from being injured in a car crash. Our next topic, we're going to spend a little bit of time on how do we describe the motion of falling objects. Well, an object is falling. Obviously, it is experiencing some force of gravity. So let's write down some things that we know that we've looked at before. Remember this equation, the force due to gravity is equal to the object's mass times the strength of the gravity. Now, if we only have gravity acting as a force, this object is in free fall and we only have gravity as the force acting on it, then my net force is my gravitational force. We can also remember from Newton's second law that the net force is equal to mass times acceleration. So, if indeed there are no other forces acting on my object as I'm dropping it, it's in free fall, G is equal to A. I can show this mathematically simply by saying if the net force is equal to the gravitational force, then in this situation, then the net force equal to the gravitational force is also equal to mass times the gravitational field here, And if my net force is equal to mg, my net force is also equal to ma, then mg must be equal to ma, right here. Mass cancels out on both sides, and I am simply left with A equals G. So you can see these are very closely related. And indeed, when I'm talking about an object that's falling in a free fall motion, where gravity is the only force acting on it, then my force equals mass times acceleration can easily be substituted with my acceleration is the acceleration due to gravity only, which is 9.8 meters per second squared. We can also look at this motion, and here we have the ball at t equals 0 times 0 seconds. The velocity here is 0, just as he releases it. After time of 1 second, the velocity of this ball is going to be 9.8 meters per second. After 2 seconds, it's 19.6. Here it is after 3, 4, and 5 seconds. You can see the ball is accelerating. It is gaining in velocity, and it is gaining in velocity at precisely 9.8 meters per second squared. So here I just restated that, kind of fancier font, but force equals mass times acceleration. If we're talking about the force of gravity only, it's mass times g, acceleration due to gravity. When we look at two different objects, let's say we're going to look at an elephant and an ant, and they are falling, and let's suppose that we only have the force of gravity acting on both of them. That means that the friction from the air resistance is negligible. And so we're going to pretend that. We do that a lot in physics. We kind of set up scenarios and we assume things like that. In those cases, their acceleration due to gravity, what would you expect it to be? Would you expect it to be the same or different? Would you expect that elephant to hit the ground first, or would the ant hit the ground first? Now, if we travel a short enough distance down, that air resistance really truly is negligible, and these objects really would hit the ground at the same time. You could look at two different sized balls, for example, that would give you a really good idea. A bowling ball and a tennis ball or something. They have very different mass, probably similar amounts of air resistance there. And drop those and see which one hits first, or do they hit at the same time? They should hit at the same time. Now, how can that be true if the force due to gravity on this large object is 10,000 newtons, but the force due to gravity on this object is only 10 newtons? Well, the force due to gravity on this object is so much more because this object has so much more mass, 1,000 kilograms of mass to be precise. And this object doesn't have as much force due to gravity acting on it because it only has 1 kilogram of mass. So remember that the force due to gravity is related to the mass of the object, but the acceleration due to gravity is going to be the same for all objects close to the Earth, because all objects close to the Earth are minuscule compared to the Earth itself. And when we look at this, if we rearrange our equation, we know that force equals mass times acceleration. If we multiply both sides by, divide both sides by the mass, then we can rearrange this to be force over mass equals acceleration. The mass on top and the mass on bottom cancel out. So I can simply rewrite my equation, force equals mass times acceleration. If I'd like to just talk about acceleration, I can do that. I can say acceleration equals force divided by mass. I've just restated that equation in a different way. And when I do that, and I substitute in my force due to gravity and the masses of these objects, yes, indeed, the force due to gravity is greater here than here, but so is the mass. And it ends up that my acceleration due to gravity for all objects close to the Earth is the same, 9.8 times, well, if you round it up to 10 meters per second squared, or 9.81 meters per second squared. So, in the real world, when we are very close to the surface of the Earth, we encounter atmosphere, and atmosphere is made up of lots and lots of little tiny molecules. And that comprises what we call air resistance. Air resistance is a friction-like force that opposes the motion of objects moving through air. It acts in the direction opposite to the motion of an object's motion. So if an object is simply in free fall down, the air resistance acts in opposition to that movement, to that motion. The amount of air resistance definitely depends on the size, the shape, and the speed of the object. It also depends on properties of the air. There are other components that affect air resistance: the amount of moisture in the air, amount of water molecules present, the density of the air itself, how many molecules are in the air. All of those will definitely affect air resistance. Air resistance is the reason that this feather would fall at a different rate and fall more slowly than other objects. There is so much surface area on that feather that it creates a tremendous amount of air resistance. In general, the more spread out an object is, the more air resistance it experiences. And you can try this using a paper bag or a piece of paper. Crumple one up very tightly in a wad. Will experience far less air resistance than you kind of crumple a paper but sort of spread it out. Will have a lot greater air resistance. Try dropping both of those and see which one experiences more of that opposition to its downward motion. And that brings us to this idea of terminal velocity. Terminal velocity is simply the very maximum speed that an object can reach when it's falling through a substance like air. It will reach a terminal velocity. And the idea would be that, let's say we release our object initially right here. We have our object, we release it. It's experiencing the force due to gravity. As it continues to accelerate, it is going to begin to also experience the forces due to the air resistance. And this will increase as the object continues to accelerate, to such an extent that at some point the object will reach its terminal velocity, where the force of gravity is equal to the force in the opposite direction from the air resistance. And obviously, terminal velocity depends definitely on the size, the shape, the mass of the object. For example, the terminal velocity of this skydiver will be much greater than the terminal velocity of this skydiver with the parachute opened up. That will be a very different terminal velocity. This is just an example reiterating that point about terminal velocity. It is showing free body diagrams for the elephant and a feather. And free body diagram is just a force diagram showing the forces, all the different forces that are acting on that particular object. And you can see that the force of the air resistance and the force due to gravity, they change for the elephant from here to here. We have a little bit more air resistance, a little bit more, yet the elephant never reaches its terminal velocity because the force of the air resistance has not yet become equal to the force due to gravity. Whereas you can see the feather reaches its terminal velocity very quickly. After only 2 seconds, the force of the air resistance is equal to the force due to gravity, and it's already reached its terminal velocity. Now that brings us to this idea of free fall. What is free fall? Free fall is simply the movement of an object in which gravity is the only force acting on it. We assume no air resistance, and gravity is the only force in effect. Some examples of free fall. The Earth orbiting around the sun is an example of free fall. If the Earth did not have a velocity that was perpendicular to the gravitational force, it would fall right into the sun. Satellites are orbiting in free fall around the Earth. Those are examples of free fall. One kind of fun idea that comes out of this idea of free fall is weightlessness. And weightlessness, nothing is truly weightless. We're being acted on by gravity. And I apologize for that thunder in the background. I'm trying to record this and shut it off in the middle of the thunder. It's my ear little thunderstorm back there. When people say that astronauts say that are in the space shuttle are experiencing weightlessness, they aren't. They are just experiencing less force than they would experience on the Earth. Typically, it's about 90% of the strength of Earth's surface that is experienced in on an orbiting shuttlecraft. So they're just experiencing much less force, but they still experience force. What about when you've been in an elevator? You know this, and I always thought it was fun to jump in an elevator because you can kind of see, I don't know, it has a fun motion to it. Here, this girl is just standing. She's her normal weight. There's no acceleration going on. The elevator is standing still. But if we have an acceleration going up, this elevator is going up, experiencing acceleration in the upward direction. That's opposite of gravity. If she were to be standing on a scale, that scale would show that she was having a greater than normal weight. This would be definitely greater weight than she was experiencing here, greater force. If, in fact, the elevator is going down and she's standing on a scale there, she's going to see that the scale shows less than her normal weight because she's traveling in the same direction as the gravitational force. If, however, she gets to go fast enough so that she is traveling, maybe it's a really tall building, and she ends up accelerating at something around 9.8 meters per second squared in this elevator, she will experience weightlessness. At that point, the acceleration that she is traveling is equal to the acceleration due to gravity, and she will experience a feeling of weightlessness. In fact, her scale will show zero weight because she will be traveling at the same acceleration as the acceleration due to gravity, and there will be no force that will register on that scale. Here are a few advanced ideas. If you didn't do this before, what are some of the adverse effects of the health of astronauts experiencing quote-unquote weightlessness? What problems happen when those conditions are what people are living in? Or design your own parachutes for small falling objects. Test to see which one provides the most air resistance. Explain why and show me the results of that. You could identify the force that opposes gravity and enables objects to float in water. Explain how this happens. I look forward to seeing you in class and seeing what you come up with.